Greetings and welcome in. My name is Jason Ostanek. Today we'll talk about vector operations. Before we talk about vector operations, let's introduce scalar and vector fields. A scalar field is a function that takes a single value at each point in the domain. In this example, my function is phi, and it depends on three independent variables, positions x, y, z. Your functions may depend on time as well. Vector fields, on the other hand, take multiple values at each point, and vectors are denoted either using boldface font or using an arrow above the symbol, or the unit vectors I, j, and k will use a hat symbol. Some example scalar fields you're likely to encounter in fluids problems are pressure, temperature, turbulent kinetic energy, species concentration, and so on. And some example vector fields you're likely to encounter in fluids problems are velocity and vorticity. We can expand the vector field into its components. F1 is the magnitude of the vector in the x direction. I carries the direction, that's the unit vector in the x direction. F2 is the magnitude in the y direction. F3 is the magnitude in the z direction. The velocity vector usually uses a capital V symbol, and the components are typically represented using u, v, and w for the x, y, and z components of velocity. Okay, I've opened up an interactive tool called the Vector Operations tool. Again, you can toggle between light and dark mode if you prefer, and I'm going to zoom in so it's a bit easier to see. Now, this tool is really to study some advanced operations that we'll look at in a different video, but I wanted to use this tool to illustrate the difference between a scalar field and a vector field. Right now I've got scalar field selected, and I can select different functions. Let's use x squared plus y squared as an example, and I can see the scalar field here. So again, the field has a symbol phi, so my function is phi, and the value of phi, I can see that as I hover the mouse around this contour plot. The red is positive values, the gray is near zero. If I pick a different function, now I've got some blue contours. The blues are negatives, the reds are positives. So I can see that in my scalar field, which in this case depends on only x and y position, anywhere in the field, I see the function takes a single value. Okay. Now let's take a look at vector fields. So now my vector field f is equal to x comma y, and I see that the field is represented with vectors. These arrows represent both the direction and the magnitude. Larger arrows means larger magnitude. And this particular function says the x component is equal to x and the y component is equal to y. So as I move the mouse around, I can see at 0, 0, I can't quite get there, but you get the idea. If x is 0 and y is 0, my vector components are both 0, 0, and I can see in parentheses where my mouse is hovering, I'm at 0 and roughly 0. And if I scroll over here to the right, I see my x value is now 1.75-ish, and y component is still 0. So everywhere in the domain, my vector field has multiple values. In this case, I have an x and a y component, and the x and y component themselves depend on the x and y positions. Now I could have a vector field that includes three components. Right now I'm just looking at a two-dimensional plane, but there might be a third vector component that's pointing in and out of the page. And my vector field might depend on x, y, z, might depend on time. So I've got a two-component vector field, so it's got an x and a y component, and my field depends on x and y. So there's no z component, and there's also no z dimensional dependence. Let's try some other vector fields. You can see the vectors are aligned in this circular pattern. Here we've got a vector field where the x component depends on the y position. So go ahead and open up the tool, try different scalar and vector fields. Okay, so the first vector operation I want to cover is scalar multiplication. I'm not going to cover vector addition and subtraction. You can look those up on your own. I'm going to start with scalar multiplication. And what we have with this operation is a vector field multiplied by a scalar field. Now, in this case, I'm just going to consider our field values at a single point. So let's say we've got our vector field f like we were just looking at. It's got an x component, it's got a y component. I know that this vector field might change over my domain, but I'm considering a single point where I've got x component f1 and y component f2. If I multiply that f by a scalar value phi, I multiply each component by phi. So f1 multiplied by phi and f2 multiplied by phi. At this point, phi is just a constant value, so I'm just scaling each component. And expand it out in 3 dimensions, scalar multiplication looks like this. Your x component of your scalar field times the x direction unit vector times your scalar. And the same thing for the y and the z directions. And as a result, what we end up with is a vector field. It's just each component multiplied by the scalar, and the commas tell us it separates my x, y, and z components. So we start with a vector, we multiply by a scalar, and we end up in a vector. Okay, the next vector operation to cover is the dot product. I can see the dot operator right here. I have a vector f and a vector g. They are dotted together. And the first thing I want to point out is if I take a look at this part of the result here, f1 and g1 are the x magnitudes of each vector. f2, g2 are the y magnitudes, the y component magnitudes, and f3, g3 are the z component magnitudes. All of these are scalar values. There's no direction component with any of these. So the result of a dot product is a scalar value. Second, we can represent the dot product using a geometric definition, or we can use this component form here. I'm going to start with the geometric definition, and then we'll talk about the component form. Okay, first let's take two vectors. I've got a vector f. It's got an x component of 4, a y component, and a z component of 0. So this is lying along the x-axis. G has an x component of 3 and a y component of 4, and no z component. So to take the geometric definition, we need the magnitude of each vector, and we also need the cosine of the angle between the two vectors. So the magnitude of g, take g1 squared plus g2 squared plus g3 squared, and take the square root of that sum, and I can tell this is a 3, 4, 5 triangle, so I know my magnitude is 5. And the magnitude of vector f is 4. The angle between these two vectors is 53.13. So I can just go ahead and plug these numbers in, and I get a result of 12. Now, one thing I want to point out is g cosine theta, theta being the angle between the two vectors, g cosine theta is the projection of vector g onto vector f. So in this case, where f is lying along the x-axis, the projection of g onto f happens to be the x component of g. It's 3. So if I take g cosine theta, I end up with a value of 3 and multiply that with the magnitude of vector f. So 3 times 4 is 12. Okay, let's go ahead and draw out the 3 unit vectors I, j, and k. So I has a vector components of 1, 0, 0, j is 0, 1, 1, and k is 0, 0, 1. And what we can do now is let's apply this geometric definition to the unit vectors. So each one's got a magnitude of 1, and their directions, of course, are perpendicular to one another. So let's consider I dot I. The magnitude of I is 1. if I substitute the vector I in for both f and g, I have 1 times 1 is 1, and the cosine between the two vectors, well, if they're lying on top of each other, the angle between them is 0, and cosine 0 is 1. So with this geometric definition, I get a value of 1 when I dot the unit vectors with themselves. And if I have any other combination, let's do I and j. So each one, substitute I for f and j for g. Each one has a magnitude of 1. So I have 1 times 1. Cosine of the angle between them is 90. Cosine 90 is 0. So I have 0 for all other combinations. And I get the identity matrix. Now what we can do is we can expand the vectors f and g. So let's expand f. So I've got IF1, JF2, KF3, and I'm going to dot that with each term over here, IG1, JG2, KG3. And when I take each one of these dot products, I end up with I dot I, which is a vector operation, and these two scalar values are multiplied by that dot product. So I dot I is 1, I dot J is 0, I dot K is 0, and so on. And we can cancel out the terms where we've got two different unit vectors. And the only surviving terms are the terms where I have the unit vectors dotted with themselves. And of course, the result of that dot product is a scalar value. Each one is 1. So I dot I is 1, J dot J is 1, K dot K is 1. And we end up with the component form of our definition, F1G1, F2G2, F3G3. Let's go ahead and work two more examples of the dot product. We'll use the component form for this. I've got vector f with components 2, 0, 0, vector g with components 0, 1, 0. So if I use the component form, I'll have f1 times g1, so 2 times 0 is 0, and then f2 g2, 0 times 1 is 0, and then f3 g3, 0 times 0 is 0, and as a result I get 0. One more example, we've got the same f vector, but now our g vector is 1, 1, 0. So f1 times g1, 2 times 1 gives us 2. And then f2, g2, that product gives 0, and f3, g3, that product gives 0. So in this case, the result is 2. Okay, the last vector operation for this video is the cross product. Here we have vector f cross vector g. The first thing to note is that we've got a vector as a result. So I've got scalar quantities in here. These are just, again, these are just the magnitudes of each vector in the different directions. So magnitude of f in the y direction, magnitude of g in the z direction, and so on. They're separated by commas, which indicates that this term here is the resulting vector's x component. This one here is the resulting vector's y component, and then z component. We could use the I hat, j hat, k hat as well, that different nomenclature, that would work too. But this is the way I'm going to show the component form. So the first thing is that the cross product of two vectors results in a vector. And like dot product, we've got a geometric definition and a component form. Now the geometric definition looks similar, it's a little different. We've got the magnitude of f times the magnitude of g, that's similar to dot product. But now we take the sine of the angle between the two vectors, and we've got an n hat. This is a unit vector that carries its own direction. It's not aligned with the x, y, z axes per se. It depends on your two vectors. So let's take a look at this example here. I've got vector f. It's got components 4, 0, 0, so it's aligned with the x-axis. G has components 3, 4, 0, so it's in the xy plane. It has no z component. And again, this was from our previous example, so the angle between these is 53.13. So yes, we could take the um, magnitude of f, the magnitude of g, and the sine of the angle between them. The n hat vector, it's a unit vector, so it carries magnitude of 1. It's perpendicular to both f and g. So whichever plane these two vectors lie in this case, they both lie in the xy plane, but these are arbitrary vectors. They may not be aligned with the global Cartesian planes at all. n hat is perpendicular to the plane that these both lie in. Now, if the two vectors are lying on top of one another, then n hat is undefined, but that's okay because the angle would be 0 and sine of 0 would be 0. So even though n hat would be undefined in that case, the cross product would be 0 when your vectors are aligned with one another. The other thing about the n hat vector is the direction is set with the right-hand rule. So we know that this n hat vector is going to be perpendicular to both f and g, but I don't know which direction it's facing. So in this case, f and g both lie in the xy plane, so I know n hat is going to be aligned with the z-axis, but I don't know if it's pointing in positive z or negative z. To determine that, we use the right-hand rule, and the order of the cross product becomes important. Since we're taking f cross g, we start with our right hand. I like to use my fingers pointing out. I've got my palm up in the air. I'm pointing my fingers in the F direction. And then I curl my fingers towards G, and my thumb is pointing out of the page, which I tried to represent here. So n hat is in the positive Z direction in this case. But if we had taken G cross F, then your fingers would be pointing in the direction of G, you curl them towards F, and your thumb would be pointing into the page. So unlike dot product, I guess it's important to note that the dot product, it doesn't matter if you reverse F and G, but with cross product, the order definitely matters, and the sign of n hat will change. Okay, so an easy way to remember the component form is to treat this essentially like a determinant. So I've got the determinant here of this 3 by 3 matrix where the top row is the unit vector. The middle row is our first vector components, f1, f2, and f3, and the last row is the g vector components. So to expand this like you would a determinant, I just took this 3 by 3, copied it, and pasted it next to one another. This is the way I like to do it. It's very convenient. So for the x direction, we're going to start with our x direction unit vector I. And let's start with I and go diagonally down and to the right. That gives us our a positive sign on the first term. So I times f2 times times g3 is positive, and then going diagonally down and to the left gives us our negative term. It's down and to the left, so it's negative. So that's f3 times g2. I use these little circles here to show the two terms. I'll take them away, and we can do the y component next. So we need our j, that's our y direction unit vector. So I'll go diagonally down and to the right. That gives us f3g1. And then let's use this j down and to the left. f1g3 carries the negative sign. And finally for k, I've got k f1g2. And then diagonally down and left, I've got k f2g1, and that carries the negative sign. So that's an easy way to remember how to arrive at the component form here. Let's work a couple examples. I've got vector f, 2, 0, 0 are its components, vector g, 0, 1, 0. And first, let's use the geometric definition to find the cross product here, okay? The magnitude of f is 2. The magnitude of g is 1, so I've got 2 times 1. The sine of the angle between these, sine of 90, is 1. And n hat, let's figure out what our direction vector is. This problem was clearly set up for simplicity here. F happens to lie along the x-axis, G along the y, and I've got F cross G. So if I do the right-hand rule from F to G, my n hat is aligned with the z-axis, and the sign is positive. So my result is the entire calculation is aligned with the z-axis. I don't have an x and a y component because n hat is perfectly aligned with the z-axis. Right? So 2 times 1 is 2, times 1 is 1, and that lies in the z component. Here, let's work another example, but let's use the component definition here. So by the way, I use bold lines here to show the x, y, and z components. The vector f now has 3, 0, 0, and the vector g has 1, 1, 1. So these dashed lines help illustrate that this vector g, it's got a value of 1 in the x direction, a value of 1 in the y direction, and 1 in the z direction. Okay, so the dashed lines help visualize where this thing is in space. So let's go one by one. Let's start with the x component, f2, g3. So 0 times 1 is 0, minus f3, which is 0, so I already know that term's going to cancel out. My x term is 0. Let's do the next y component here. f3 is 0, so that term is 0, minus f1 g3, so minus 3 times 1 gives me negative 3. And finally, f1 g2 gives me 3 for this term, minus f2 g1 is 0. So I get a positive 3. Okay, that's it for this video. Thank you very much for watching.